this video, we're going to talk about independent and mutually exclusive events. So let's talk about independent first. Two events A and B are independent if the knowledge that one occurred does not affect the chance the other occurs. In other words, one occurring doesn't affect whether or not the other one's going to occur. All right, they're independent of each other. The example they gave is that when you roll two rolls of a die, the die doesn't care what you rolled the first time when it goes to roll the second outcome. All right. So if you get a one the very first time you roll the die and then you roll the die again, the odds that you get one don't change the second time. You still have a 1 out of 6 chance of getting a one the second time, which is the same odds you had the first time. So that would be an example of independent events. We can show events are independent with these three little bullet points here. So the first one is the condition that A will happen, the probability that A is going to occur, given that the event B has occurred. Well, if A and B are independent, then it doesn't matter that B occurred. A occurring doesn't care about B. Therefore, the probability of A given B is just the probability of A, because A could happen, the same probability, regardless of whether B happened. Like with the die. When I'm wondering what's the probability I'm going to get a one, the first time I roll a die, it's 1 out of 6. And the second time I roll a die, it's 1 out of 6. It never changes. It always stays 1 out of 6. So the probability of rolling a one stays the same regardless of the events of what happened before rolling the die. So the same would be true if it's reversed. The probability of B given A is just going to be the probability of B. Doesn't matter that A has happened. They're independent of each other. A does not affect whether or not B occurs. And this last one here is a kind of useful formula. The probability of A and B ends up equaling the probability of A times the probability of B. So we find their probabilities individually and multiply them together. That's how we can check whether or not events are independent. If they're not independent, we'll say that they are dependent. So let's look at this example here. A bag of marbles. I always wonder if students know what marbles are. Marbles are little solid balls that usually come in pretty colors. Okay. You can Google it if you don't know. But we have a bag of marbles. 10 of them are red, 12 are green, 6 are yellow. So I want to know what the probability is of drawing two yellow. So when you're talking about drawing two yellow out of the bag, what's the probability that that's going to happen? First, I kind of noticed that yellow has the least amount of options, right? Like I'm least likely to draw yellow compared to like green. So there's twice as many green as there are yellow. By the way, let me go ahead and make a note here that there are 28 total marbles in this bag. Okay, so if I want to know the probability of drawing a yellow twice, two different yellows, it kind of means like I'm holding, I put my hand in the bag, I draw out a marble and it's a yellow. And then maybe I grab my other hand into the bag and I draw out another marble and it's a yellow. So I'm holding both marbles in my hand at the end. That's the difference between replacement versus without replacement. So in this scenario, it would make sense that it's without replacement. I'm holding both marbles in my hand at the end. So in that case, then the probability of drawing a yellow the first time in the first draw is going to be 6 out of 20. That's just the probability of drawing a yellow in general, 6 out of 28. But to draw a yellow again, given that I drew a yellow already, okay, so drawing a yellow for the second marble, given that I drew a yellow for the first marble, that's going to be a little bit different because now that I have one marble in my hand, okay, I have a yellow marble in my hand, there are less yellow marbles in the bag. There's only 5 yellow marbles. And actually, there's less total marbles too. There's no longer 28 marbles in the bag, there's now 27. So you'll notice that these are not equal. And I've kind of showing that based on this discussion up here, okay, that the condition doesn't equal the probability of just drawing a yellow in general. Okay, so drawing a yellow second is affected when I draw a yellow first. But I could change those odds by making them independent if I use replacement. So if I replace the first marble, now it changes, because now the probability of getting a yellow the second time, knowing that I drew a yellow the first time, is still going to be 6 out of 28, because I put the yellow marble back into the bag. So there's still 6 yellow marbles out of 28 total. And that does equal the probability of getting a yellow. So these are independent when we have replacement. Okay, so let's go ahead and look at a standard deck of cards. In a standard deck of cards, there's 52. They kind of take this example to explain what's in the standard deck of cards. There are 4 different suits in the standard deck. There's clubs, spades, hearts, and diamonds. And there's 13 cards in each of those. They're counting the aces as ones, by the way. Okay, so they're counting these as ones in this example. And then 2, 3, 4, 5, all the way down to 10. And then they have what are called the face cards, Jack, Queen, and King. Okay, so you can kind of use this to refer to if you're not as familiar with the standard deck. They want to know, suppose you draw 4 cards without replacement. Which of the following outcomes are possible? And then re-answer this with replacement. So if I look at part A here, when they say QS, that means I have a queen of spades, okay? And then I draw a 1 of diamonds, which would be the ace, a 1 of clubs, again, an ace, and queen of diamonds. This is totally possible. So this is possible without replacement. And I'm going to use the shorthand notation for without. And then, of course, it'd be possible with replacement as well. If you're putting the cards back in, that's totally possible. It makes sense. There's nothing weird about that scenario. The next one is a little weirder, though, because in this one, they're saying you grab a king of hearts, a 7 of diamonds, a 6 of diamonds, and another king of hearts. That's a problem, because we already drew a king of hearts and it's out of the deck now. There's not 2 king of hearts, there's just 1. So this is not possible without replacement. Oops, not possible. Let's make it 2 separate words there. Possible without replacement. But of course, all of these are possible with replacement. So that makes no difference at all. All right. So let's look at mutually exclusive events now. So mutually exclusive events cannot occur at the same time. This means that they share no outcomes in common, and the probability of getting an A and a B at the same time, those 2 events, is 0. It's impossible to happen. So let's look at an example here. So we have a sample space S, which is the numbers 1 through 10. And then we are given that the set A is 1 through 5, the set B is 4 through 8, and the set C is 7 and 9. So they ask, are A and B mutually exclusive? And the answer is no. No. So A and B are not mutually exclusive because they have something in common. What they have in common is 4 and 5. Since they share the outcomes 4 and 5. Okay, are A and C mutually exclusive? They are mutually exclusive. A and C are mutually exclusive since they share no outcomes in common. Now, that means then that the probability of getting A and C is 0. It's impossible to happen. That's what it means to have a probability of 0. It's impossible. They share no outcomes. No outcomes. All right. So that's the idea behind whether or not they're mutually exclusive. And there is a quick note down here. If it is not known if A and B are mutually exclusive, assume they are not. In other words, assume they have something in common until you know otherwise. All right. We'll just make sure that we make that assumption for the sake of using what we'll see in the future is the more general version of a formula when we don't know if things are mutually exclusive.